In this video, we're going to do some examples of Lewis structures that require a double bond or a triple bond in order to be a complete Lewis structure. In the previous video, we did examples of single bonds. So let's go ahead and take a look at a quick refresher of what double bonds and single bonds and triple bonds are. So when we look at these bonds, these are electrons that are shared between two atoms. And sometimes you might have what's called a single bond, which is simply two electrons being shared, and that's represented by a single line. Or you could represent it, I'm just going to draw two atoms sharing electrons like this. So this would be a single bond, or again like that. A double bond, on the other hand, is when you're sharing two pairs of electrons, or 4 electrons total, and it's represented by a double line. Let's do it in a different color so we don't get confused there. It's a double line instead of a single line. And so it might look like this. You have 4 electrons here, but we represent it by these lines instead. And their bonded electrons are shared between two atoms. And then lastly, you might also have what's called a triple bond, where you share 3 lines. In other words, you're sharing a pair per line, 6 electrons. So it looks something like this. This is 6 electrons being shared. And I'm just going to draw it in a different way, but it's the same thing. 6 electrons being shared like that. And we draw each of them, each pair as lines instead. So that's our 6 electrons being shared there in a triple bond. And we're going to take a look to see when we need to use triple bonds in molecules. So let's go ahead and try an example such as carbon dioxide. So we're going to draw carbon dioxide, and we're going to see if it needs multiple bonds, single bonds, so double or triple, for example. We're going to follow the same first few steps, figure out the number of valence electrons. So 4 valence electrons for carbon, and then oxygen in group 16, so 6 valence electrons times 2. That's 12 valence electrons to place, but total we have 16. 4 plus 12 is 16 valence electrons to place. Our central atom is going to be carbon. It's the one we have least of. There's more single unpaired electrons in carbon if you were to draw a Lewis structure. So for example, carbon would look like this compared to oxygen, which is like this. And also carbon is the least electronegative between the two. So let's draw our central atom, and then we'll put our peripheral atoms around it. And we're going to connect them by single bonds, like that. I'm just going to move this aside here so we have some room. So now that we've placed these single bonds here, we've placed 4 electrons because it's 2 electrons per bond. So we placed 4 electrons, and that means we have 12 electrons left to place. And so we'll start putting them around the central atom, the peripheral atoms, until they're happy. So 1, 2, 3, 4, 5, 6. Now that oxygen's happy because it has 6 surrounding it plus the 2 in the bond, that's 8. 1, 2, 3, 4, 5, 6. This oxygen is happy because it has 6 surrounding it plus 2 in the bond, that's 8. But now notice we've placed 12 electrons total, we have 0 left to place. And we have to check if everyone's happy. Oxygen is happy, and so is this oxygen here. However, what you'll notice is that the carbon is not happy. Carbon only has 4 electrons now because there's 2 lines there. And so that's not really helpful for carbon. Carbon needs to have 8 valence electrons to be happy. It needs a stable octet. Now we ran out of electrons, so we can't create any new ones. But our peripheral friends can help us. So this oxygen on the right side will say, you know what? Instead of having a lone pair for myself, I can share these with carbon. And so when it does that, it'll look like this. It'll be a double bond, then the remaining lone pairs there. Now we can go and continue and look. We can say, well, is carbon happy now? And right now, carbon is a bit happier. It has 6 because there's 2 in each line. So there's 3 lines, 6. The other oxygen that shared here, that one's still happy. It had 4 lone electrons, or 2 lone pairs. That's 4, plus the 2 per line there. So 2, 2. That's 8 total. So that one's still happy. Like, just sharing doesn't make you less happy. You're still happy because you still have your full shell. But now carbon is still not happy. Carbon still needs some help. And it's not fair that the oxygen on the right has to do all the helping. So the oxygen on the left can do some helping and say, you know what? I'm going to donate some of my electrons. I'm going to put them into a shared pair as well, and hopefully carbon will be happy then. So when that happens, we get a double bond here from before. And now this one has a double bond as well. All oxygens are happy. And now carbon's happy. It has 4 lines surrounding it. And so now it has 8 valence electrons. So everything is happy now. And that's because we drew some double bonds for the carbon to be happy. So there we have an example of a double bond needed in order to satisfy the stable octet of the central atom. And we know we need a double bond or a triple bond when we run out of electrons and we still haven't satisfied all the atoms. So if you run out of electrons and you haven't satisfied all the atoms, especially the central atom, you're going to go and ask the peripheral atoms to take turns helping out and creating multiple bonds where needed. So let's do another example. This was a double bond here. So this is a double bond in here. And same thing here. This is another double bond over here. So we've drawn 2 double bonds in the carbon dioxide molecule. Let's do this example over here. We're going to try to draw the molecule HCN. So it's a bit interesting because we have more than 2 different elements here, but it should still work roughly the same way. We have, let's see, we have for carbon, there's 4 valence electrons. For hydrogen, there's 1 valence electron. And for nitrogen, it's group 15, 5 valence electrons. And we want to go with usually which one is the least electronegative one. It doesn't always have to work that way. We want to see which one has the most number of unpaired electrons. So if we look at carbon, it's like this. There's 4. If we look at hydrogen, there's 1. If we look at nitrogen, there's 1, 2, 3, 4. Okay, there's only 3. So nitrogen only has 3 unpaired, whereas carbon has 4 unpaired. So carbon looks again like it's going to be a good central atom. Generally, when you see carbon, it is a pretty good bet that that's going to be your central atom there. So we'll put carbon here and we'll put the other atoms around carbon, just like this. That's fine like that. And we'll connect them by single bonds. And so I forgot to add up the total here. We have 4 plus 1, so 10 valence electrons here to place. We've placed 2 in single bonds, so minus 2. That's 8 valence electrons left. Now, let's go ahead and place them around our peripheral atoms until everybody's happy here. So we'll do, actually, I didn't place 2. We placed more than 2. I noticed that we placed 2 bonds. See, it's very easy to make mistakes if you do it very quickly, so you have to be nice and slow and purposeful. So 10 valence electrons, we placed 2 bonds, which is 4 valence electrons. That's 6 electrons left to place. So let's go put them around our central atoms our peripheral atoms until they're happy. So 1, 2, 3, 4, 5, 6. That one's happy now because nitrogen is 6 non-bonded electrons plus the 2 in the bond. That's 8. And so we've placed that and we have 0 electrons left to place. Let's go see if our other atoms are happy though. Hydrogen, you'll notice, only has 2 because of that single bond there, but that's okay. For hydrogen, remember, it's happy with 2. But carbon, on the other hand, is not happy. We ran out of electrons and we just didn't have enough to make carbon happy. So we have to go ask the peripheral atoms for some help. Hydrogen can't really help because it doesn't have any lone pairs to put into shared pairs, but nitrogen can help. So nitrogen will say, okay, tell you what, I'll put one of my lone pairs in there. And so it will look something like this. We have H, C, double bond N, and then our lone pairs like that. Now, we'll take a look. Hydrogen's still happy. Nitrogen's still happy. It doesn't change its happiness there. Just make sure when you put the lone pairs into a double bond, you actually erase them. And you notice I moved the position of these lone pairs here. I did that just because it's going to be easier to do our drawing if we need any more bonds. So let's see. Carbon is not happy yet. It only has 6 valence electrons. And so we can ask nitrogen to maybe provide some more. So this nitrogen will say, you know what, fine, I'll put these lone pairs into there as well. And so when we do that, we get H, C, 3 lines, N, and then our remaining lone pair there. Hydrogen's still happy. Nitrogen's still happy. It has this two electrons that are not paired, or it's one lone pair. So that is the lone pair there. They're not in shared pairs, I should say. That's 2, and then the 3 lines, that's 6, so that's 8 total. Hydrogen's still happy, still has 2 from the single bond. Carbon, on the other hand, let's take a look. We have to see if it's happy at this point. It has 4 lines connected to it. That's 8 electrons. It has a stable octet. So here we were able to satisfy everyone thanks to the peripheral atoms helping out a little bit. Not so much hydrogen, but definitely nitrogen. And so we have a single bond in this molecule. We have a triple bond as well. And then we also have a lone pair on the nitrogen. And so there we drew the Lewis structure for HCN. In this video, we saw that sometimes you'll run out of electrons before all the atoms can be happy in the molecule. So what you have to do is you have to use the peripheral atoms to create triple bonds or double bonds until everybody is happy. In the next video, we're going to do some examples of Lewis structures where there's some exceptions. And those exceptions you might remember from grade 11 are the incomplete octet and the expanded octet.